Swayam Prabha. Digital India. Educated India.
So, good morning to the students, all of you.
Good morning.
So, good morning, thank you. It's one more lecture on magnetic resonance spectroscopy. I'm not going to talk about infrared today, though the title was mentioned that way. I will talk more on the nuclear magnetic resonance because there are things that we started and we did not complete. So it would be nice to go through some of the basic theoretical methods in nuclear magnetic resonance, particularly the spectra of chemical compounds, which show multiplets for each line sometimes, and also many lines corresponding to different nuclear chemical environment. Okay. So we will do NMR spectroscopy. I have sent to the lecture notes to Professor Anbarasan. I'm sure you will receive all of them. And there is another set of lectures that is on the optical spectroscopy. The lecture note that I used to explain things to you is now sent to you as a PDF file. It's handwritten. The PDF file is also with you, and there are about 70 or 80 multiple choice questions in optical spectroscopy, that is in microwave, rotational, vibrational, and basic spectroscopy. There is also a set of lectures which I had recorded earlier, and I also offered an online course called NPTEL spectroscopy course. So I have sent you the link for that course, and all the lectures are downloadable from the website. Therefore, I would spend more time on things which I have not recorded so far, that is the nuclear magnetic resonance spectroscopy today. Okay, so let me share my screen, and should be able to see my screen right now, and also the PDF file which says chemical shift. Are you able to see that file? Elementary nuclear magnetic resonance spectroscopy. Command. Let me do that. Let me see if I can do that. Yeah, so you should be able to see the full lecture file. Yeah?
Yes, sir.
You can see that, right? Right now. Yeah, okay, good. So I would start with the basic reason why chemists were initially interested in the nuclear magnetic resonance, even though the nuclear spin property was of more interest to the physicists to study the nuclear properties and also solid state, the nuclei in crystal lattices and the lattice phenomena. But chemists got involved almost in 1949 or so, right after the few years after the magnetic resonance, 2-3 years. And that is primarily because the molecules started showing spectral lines corresponding to nuclei of different chemical environment. Okay, so let us see that. The reason for that is, you know, the Larmor frequency. Last time I explained to you that the Larmor frequency is proportional to the magnetic field, applied static magnetic field, and also it is a property of the nuclear gyromagnetic ratio. And gamma H naught is the Larmor frequency, and that is assuming that the nucleus sees the entire H naught, the magnetic field, which is externally applied. But the nucleus does not, because it is surrounded by electrons. And the electrons are sort of moving electric fields and rotating electric fields, and therefore they generate local magnetic fields. And these magnetic fields may also add to the external magnetic field or work against the external magnetic field so that the nucleus does not see the entire H naught but slightly different H naught. You can see that. That's what is the statement. The field experienced or seen by the nucleus is often different from the applied field because of the local magnetic fields. That may shield the nucleus from H naught. Okay? Let's do that. And this is due to the magnetic coupling. That is the electron associated, the electron surrounding the nucleus. So there are multiple possibilities by which this happens. One is that the electrons introduce a magnetic field at the nucleus due to the motion of the electric charges, that is the electronic charges, the orbital motion. Orbital motion brings in a magnetic field at the nucleus, which is against the external field, which shields the nucleus from the external field. The second is that the magnetic fields of the electron, due to the magnetic moments associated with the electron spins. Okay? So one is the motion of the orbital motion, the other is the electron spin motion. The electron spin is an intrinsic property of the electron, a spin a half system, and therefore those magnetic fields can also interfere with the nuclear magnetic field. And the third is that the spin of the nucleus itself interacting with the spin of the neighboring nucleus, okay, through bonds or through primarily proximity in space. So you can see that carbon-carbon bond, if you have a C13 nucleus, it is a spin a half nucleus. C12 does not have any spin, therefore C12 is inert. It does not respond to NMR. C13 is the spin a half nucleus, and if there is a nearby C13 spin a half nucleus bonded to it, it is possible that these two nuclei interact with each other and due to the bond. It's possible that there is also a hydrogen connected to the carbon in some other carbon, which is sort of bent towards this carbon. So spatially, they get closer to each other. Though there may be a hydrogen here, carbon here, hydrogen. These two hydrogens will be spatially close to each other. They can also interact with each other. So either through space or through chemical bond, these magnetic fields interact, and therefore these magnetic fields shield the nuclei from the external magnetic field. So all these things, B and C particularly, give rise to coupling between nuclear spins or between electron and nuclear spins. Therefore, you can see that if the electronic density or the electronic environment around the nucleus is different, then you are going to have different magnetic fields. If the magnetic fields are different, please understand that the absorption frequency, the resonance frequency is gamma H naught. But if it is not H naught, for nucleus 1, maybe H naught prime. And for nucleus 2, it is H naught double prime, something else. Therefore, you could see that these two nuclei absorb at two different energies. The radio frequency field, which raises the spin from one lower energy level to the upper energy level, has the frequency corresponding to this. Therefore, if that frequency is the same by the coil, suppose 100 megahertz, that frequency is generated by the coil. Now, the gamma H naught should be equal to 100 megahertz. But if you put in the H naught, and if the gamma H naught is only 90 megahertz, then you must increase your magnetic field. Therefore, if you increase the magnetic field until it reaches the gamma H naught value of 100 megahertz, there is no resonance. Okay? So you can see that the resonance frequency is directly related to the shift in the magnetic field. We will see that number in the equation below. Okay? So the equation below is like this. Okay? Let's see if we can do this. So the shift that corresponds to the shift in the frequencies, this is called the chemical shift. And the shielding of the magnetic nucleus, spin magnetic nucleus by the external field, these local fields, is called chemical shielding. Now, let us calculate an applied magnetic field for 1.4 Tesla. What is the proton resonance frequency? This is now getting into the practicals. And these kind of things you must do. Otherwise, you will not be able to follow. So let me do the following. Just 1 second. Yeah, I think you are still able to see the whole thing, right? Yeah?
Yes, sir.
Yeah, okay. So let's look at the proton frequency. So let us look at 1.4 Tesla, which is the applied magnetic field. And then you know the gamma value for the proton is 26.75 into 10 raised to 7, which is 2.675 into 10 raised to 8 radians per Tesla per second. That's a gamma value. And the field H naught is 1.4 Tesla divided by 2 pi, because this is angular frequency. Gamma H naught is angular frequency. So if you divide this by 2 pi, you get to the linear frequency of the coil, the resonance frequency of number. So if you do this multiplication, 1.4 Tesla is 1.4 times 2.675. And then you have divided by 2 pi. 2 pi is about 6 point something. So you have close to 3.6 by 6, which is about 6. And then 10 raised to 7 per second, which is 60 into 10 raised to 6 hertz or 60 megahertz. So the proton resonance frequency for a field of 1.4 Tesla is 60 megahertz. I hope you follow this right away. And for carbon-13, remember, the gamma value for the carbon-13 is approximately 1/4 of the gamma value. Please remember, this is 6.728, but this is 10 raised to 7. This is 2.675, but it is 10 raised to 8. So for this, 26.75 into 10 raised to 7. So 26.75 is 6.7, is about 4 times. Therefore, you see carbon-13 frequency is 4 times less because its gamma is lower. And so you can see that the resonance frequency for carbon-13 is 15 megahertz. Now, you can do NMR by 2 methods. You either fix the field, magnetic field, H naught. If you fix the field as 1.4 Tesla in the coil experimental methods, then you see proton will absorb at 60 megahertz, carbon-13 will absorb at 15 megahertz. So you must have a radio frequency field which is changing so that the radio frequency field reaches 15 megahertz, carbon-13 gets absorbed. If the radio frequency field raises to 60 megahertz through the radio frequency coil, then proton gets absorbed. So this is one experiment. The other experiment is you fix the frequency of the coil. Electronically, it is easier. Okay? The frequency, the coil will generate 60 megahertz only, for example. Therefore, for getting proton to be excited, you must apply a magnetic field of 1.4 Tesla. But if you want to get carbon-13 at 60 megahertz to be absorbed, please remember, the magnetic field should be 4 times this. So instead of 1.4 Tesla, you must change the magnetic field to 5.6 Tesla. Then only carbon-13 will absorb at 60 megahertz. So there are 2 ways of doing the experiment. Either change the magnetic field or change the frequency of the coil. I think most of modern spectrometers come with a fixed coil. And the fixed coil is the proton resonance frequency, 100 megahertz NMR spectrometer, 400 megahertz NMR spectrometer, 600 megahertz, 900 megahertz. I think today we are also past to the 1000 megahertz NMR spectrometers, very, very high resolution and extremely costly instrument. They run into several crores or maybe even tens of crores for very, very high field. Also, it is very difficult to have such high fields homogeneous without any variation, because the cylindrical tube that you have, the NMR tube, the field should not drift between this tube length. The field should be the same. So keeping homogeneous magnetic fields at very high magnetic fields is also a technology challenge. And today we use superconducting magnets. Superconducting magnets are among the most stable, and you need, the price you pay for that is you need to keep the superconductor below 4 Kelvin, which means you need liquid helium. And liquid helium is extremely expensive. And if you want to keep liquid helium should be surrounded by liquid nitrogen because otherwise liquid helium will evaporate much, much faster. So you need liquid nitrogen or liquid nitrogen, I think liquid nitrogen probe, and then surround inside that you have a liquid helium, and then inside you have the superconducting magnet, and then you apply the steady field. Okay. Now, this is assuming no chemical effect. The gamma is a nuclear property. So when you use this number 2.675 and when you use this 1.4 Tesla, you say that all the magnetic field that I apply can be seen by the nucleus. No electrons in between, no other nuclei. But that's not the case. For example, hydrogen atom is a proton surrounded by an electronic cloud. Therefore, the hydrogen atom surrounded by the other nuclei will have a different resonance frequency. So you can see that the new resonance frequency of the hydrogen atom is nu naught plus or minus delta nu, and this delta nu is also proportional to the external magnetic field. Therefore, you see that the delta nu, if you call this as a proportionality constant sigma times H naught, then the H local, that is this one, is H local is H naught into 1 minus sigma. Okay? Delta nu has to be taken out. Therefore, the local magnetic field at the nucleus is not H naught, but it is 1 minus sigma. And so the sigma has shielded the nucleus from seeing the whole field. The sigma is called the shielding constant. So an example, proton in CH2, a methylene group, will have a different H local compared to a proton in a CH group, and so on. So this is for proton NMR, the same thing with carbon, the same thing with nitrogen, fluorine. In different environments, they will have different local fields. Thus, when proton NMR spectra are taken, one can identify chemically different protons in, say, for example, C2H4Cl2 is an example. C2H4Cl2 is CHCl2, CH3. This is one compound. So you can see that this carbon has a lot less electronic cloud than this carbon because the chlorine is an electronegative element. It pulls the electron density towards it. Therefore, the carbon does not see much of the electronic cloud. So the carbon nucleus is bare. It sees most of the field. Therefore, at very low fields, because your frequency is fixed 100 megahertz or something like that, the resonance frequency is achieved at lower magnetic field and not at higher magnetic field. But if the proton is shielded, if the carbon is shielded, the resonance will happen at a higher magnetic field. So you can see that this proton sees the lower magnetic field for resonance, and this carbon, I'm talking about proton, yes. This proton sees the magnetic field, all of it, but this proton sees less of it because it is now, the electronic density around it is more, and therefore the electron shield. So you can see that the proton NMR spectrum now will contain two absorption lines. A line corresponding to the this compound, CHCl2. Okay, a line corresponding to this carbon and a line corresponding to this carbon. Now, on the other hand, if the same isomeric compound, C2H4Cl2, is 1,2-dichloroethylene, dichloroethane, C2H4Cl2, where the chlorine is distributed between both these carbons, you can see that this proton and this proton have identical electronic environment. They see the same electron density because of the chlorine on either side, and they are identical, chemically identical nuclei, and therefore there is only one resonance frequency, and proton NMR spectroscopy will give you only one resonance. So right away you can see that two isomers have two different spectra. This is the chemical shift effect. This is fundamental in NMR, was discovered initially for ethanol, And later, of course, thousands and thousands of compound, today millions and millions of compound, and any organic chemist who submits a research paper following a very detailed synthesis, if he or she does not provide the NMR spectrum, proton and carbon-13 NMR spectrum, their paper is unlikely to be accepted. It's as bad as that. Okay. So today, everybody uses NMR spectroscopy to get the first level structure. See, another example is the alcohol, CH3CH2OH. You see that hydrogen corresponding, connected with the oxygen, is most depleted in the electron density. Therefore, it's supposed to have a lower frequency, but you'll be surprised that it doesn't happen that way. Okay? The resonance frequency for the hydrogen comes in between. This is ethylene. This is the methylene group, CH2. And then there is the methyl group. So, but you will see 3 proton resonance lines. Okay? And in the case of ether, which has the same molecular formula, CH3CH3O, you see that, ether has only 1 proton line because both methyl groups have exactly the same chemical environment. So, in the case of the details for methanol, ethanol, let's do that. There are 3 types of proton, 1H. The OH proton electronic cloud is pulled by the oxygen, so leaving the hydrogen exposed to the external field. Therefore, for a given absorption frequency of the spectrometer, omega naught, you see the H naught, gamma H naught is equal to omega naught, will be reached at lower value of H naught than the CH3 proton. Okay. And likewise, for the CH2 proton, is more shielded than the OH proton, hence higher magnetic fields needed to resonate the hydrogen for the ethylene, the methylene group, compared to the hydrogen of the OH. Therefore, the magnetic field required is supposedly OH smaller, CH2 slightly more magnetic field, and CH3 much more magnetic field. This is what you see as the higher increasing field direction in the NMR spectra. This is what one would expect. However, the spectrum is slightly different. Okay? And there are several reasons for this. Why methylene group goes first, and then the OH, and then the CH3. And you must, when I send this lecture notes to you, you must go through this link to find out the reason why the spectrum looks different. But what is important is you still get 3 lines corresponding to the 3 different protons. So the link above, it also gives, and there is a beautiful book which you may not have access to, but IIT library has it. So while you are here, you may be able to get an access to this book. The book is called NMR Spectroscopy by Harold Gunther. And it is a very, very detailed textbook and very practical book that it also gives you explanations. And the chemical shift data are presented in many textbooks. For example, the delta, what we call as the chemical shift. Now, how do we calculate delta? Let us look at that. Okay. See, when you say that the field is shifted, what is the compound which has the maximum shielding? What is the compound? There is a reference compound. And that reference compound happens to be tetramethylsilane. SiCH3 4 times. The tetramethylsilane has the highest magnetic field for most of the proton-based compounds. Okay? And it is also a solvent. Therefore, TMS has the highest, farthest line on the right-hand side. And that's called the reference line. So the frequency corresponding to that reference. And then the frequency corresponding to the substance. The difference between the two is proportional to the magnetic field. Now, 100 megahertz spectrometer, the magnetic field difference is this much. In 500 megahertz spectrometer, the magnetic field difference will be this much, 5 times. And so on. Now, you don't want these kind of things depending on the spectrometer. Therefore, you divide this by the spectrometer frequency, then you get a number which is independent of the magnetic field. So you see the nu of substance minus the nu of reference divided by nu naught. This is called the delta, which is a fixed number irrespective of which instrument you use. 100 megahertz you use, or 500 megahertz you use, or 1000 megahertz you use. You have divided by the spectrometer frequency there. Therefore, this number is independent of the magnetic field. This is also magnetic field. This is also magnetic field. They get cancelled out. Okay. Therefore, what you see delta is a very, very small number, extremely small. So you want to see that, you want to report these numbers every time multiplying by 10 raised to minus 6, 10 raised to minus 7, 10 raised to minus 8, etc. You get rid of that by multiplying this by 10 to the 6th. And then we call it as a parts per million, because 10 to the 6 is 1 million. Therefore, the number per million is called the parts per million, and this is called the ppm. So for proton NMR, the reference substance is the tetramethylsilane, as I mentioned to you. They have the highest shielding for all the, that means they need the highest magnetic field. Therefore, in the spectrum, when the spectrometer frequency is fixed, they happen, the absorption line happens at the farthest right in the spectrum. And as you come towards left, closer and closer to the left on this side, it is called a low field, low field, low field, which means if the carbon is connected to more and more electronegative element, if the proton is in the environment of more and more electronegative element, then it is shifted to the lower field, and so on. Now you can see that. So the shift delta for cyclopropane, all the 3 hydrogens are the same. Therefore, all the 6 hydrogens are the same. So you can see 0.22. For ethane, it is 0.88. Both the hydrogens are equivalent. Ethylene, both the hydrogens are equivalent. Acetylene, both the hydrogens are equivalent. You see that this shift. These are all experimentally obtained. And there is a quantum chemical theory to compute chemical shift. The only thing is that chemical shift, as we have reported here, is a number, but the shielding phenomena, chemical shielding, is not a number, it is a second-rank tensor. It's a physical quantity which is dependent on 2 directions, multiple directions, and therefore there is a quantum chemical theory for computing the chemical shielding constants that we will not discuss here. But that's an ab initio method for studying NMR from fundamental Schrodinger equation. Okay. Now here we have experimental numbers. So benzene, it's very, very low field because the delta is so far away. So if you say 0 here, 0.2 is here, 0.5 is here, 0.7 is here, and so on. And so if you look at it, 7 is quite far away. And then you can see methylene chloride, methyl chloride, acetic acid, acetaldehyde. So this is a list of numbers. Okay, these numbers you can find in all the textbooks in NMR, and the more accurate numbers are available on the internet. And there is a very famous site for finding some of these spectroscopic data from the National Institute of Health, NIH, sorry. It's also called the National Institute of Science and Technology, NIST, in the US. It is Maryland. They have a public domain website. You can look for most of the compounds whose data are quite verified, well verified. They are reported there, and the spectra are available. So you can also get some of these details from the website. Okay, and the other famous book for you to deal with this from a quantitative perspective is the book by Silverstein and Webster. It's called The Spectrometric Identification of Organic Compounds. And there is, there are 3 authors. So Silverstein, Webster, and David Kimley, I guess, David Kimley. So, okay, I don't know the names of the third one. I only know the book as the Silverstein's book. But there are 3 authors, and this is also very important for studying the qualitative phenomena, but with a lot of experimental relevance. Okay. Now, there are some examples in the lecture notes, okay, which I will share with you. And you can see that the spectra, for example, C6H8O, with line intensity is roughly proportional to the number of protons that you have. You can see that there is a CH3, CH3, CH, CH. So there are 2 hydrogens which are chemically equivalent. There are 6 hydrogens which are chemically equivalent. So the ratio is 1:3, and you can see that the ones which are the smaller number of protons, they are on a low field, and then methyl group is on the high field, 3. And likewise, you have CH3, CH3, CH3. What is this compound, by the way? What is it? You can always say 236, 246 trimethylbenzene, but it's not. That's also a nickname for that. Okay. So this compound, you can see that there are only two lines. So what are the two lines due to? The two lines are due to the 3 plus 3 plus 3, 9 protons as one line, and the one proton here, and the one proton here, which is directly bonded to the carbon in the benzene ring. This has a lower field, that is, it has a lot of field removed, magnetic field removed, and so for it's easily exposed. So that is this one. These 3 protons, the signal comes here on the low field, and the 9 protons, the signal comes here on the high field. And the ratio 1:3 also tells you that C9H12 has the structural formula. So there are lots of examples that you can, and it's a fantastic exercise for you to build a library of NMR compounds, simple to more complicated and so on. Try to understand why they are, and then you get to know so many more details about one of the most important applications of spectroscopy to practical world, to the practical organic, biological chemistry, and also materials chemistry, and particularly in pharmaceuticals and every other place where organic compounds are used. The spectra, NMR spectra of organic compounds are quite challenging. And chemical shift is the first of many things, okay? So let me stop with that part. Now it is almost what? Whoa, it's about half an hour, I guess, since I started. So if you have any questions or you want to stop, tell me, otherwise I'll continue. Is everybody okay with this kind of qualitative things?
Okay, sir.
Does it make sense? Does it make sense?
Yes, sir.
Have you read these things before?
Yes, sir.
So you know about chemical shifts before, right?
Yes, sir.
Very good. Okay, so I made things simpler for you without any mathematics. But the next one is going to be slightly more mathematical, okay? The spin-spin interaction, okay? How many of you have studied the multiplet structure in NMR spectroscopy? Please raise your hands. I can see all of you. I can see all of you. Wow, only 2 or 3 people. 4. The rest of you have not studied? Yes, no? No, okay. So the 4 people will be at an advantage. They will follow everything that I say, I'm sure. And all of you will find the rest very, very useful to you, and the first time when you see it. Okay, so the multiplet structure. How do you remember the multiplet structure? You remember this by Pascal triangle? How do you remember? Pascal triangle, right? One proton, it creates a doublet for the next proton. 2 protons, it creates a 1-2-1 pattern. And 3 protons, they create 1-3-3-1 pattern, right? Something like that. So that's a Pascal triangle. But Pascal triangle is just a mnemonic, that is some sort of a symbol in mind to keep the mathematics follows from the Schrodinger equation, from the energy levels, and from the quantum mechanics of it. And that is what I'm going to do for the remaining maybe an hour and 15 minutes for this morning session. Okay. Now, please remember, unfortunately, I cannot write things down because I don't have a tablet here. And I can only show you a slide. You see, I'm sitting in a place and I'm using a Mac. If I were in Chennai, the first thing I would have done is to put the Wacom tablet in front of you and then write things very slowly for you to actually follow. So now I have to show only images. So all writings I have to explain using words. Now, how many of you remember H psi is equal to E psi now for a spin-and-a-half system. 4 days ago, 4 days ago, right? Okay. Do you remember that there were 2 energy levels for a spin 1/2? Do you remember that now? And it's a transition from the lower energy to the upper energy. That's the normal frequency, gamma H naught times H, that is H bar omega naught. That's the energy between the 2 energy levels. This is for 1 spin. But if you have 2 spins, which are close to each other, how many energy levels are possible? That's the first thing. You have to think about logically, just to have a qualitative mental picture, then go to the mathematics. Okay? So suppose I have 2 spins. How many energy levels are possible? Both spins can have a lower spin, right? Lower. Both spins can be aligned with the magnetic field. 1 spin in the lower state, another spin in the upper state, right? Up and down. It can also be down and up. And then both spins can be down. So how many energy levels are there? Ideally 4. Ideally 4. But if both the spins are identical, this or this, they're exactly the same. Because you can't tell the difference between the 2 spins. If both spins have exactly the same chemical environment. Okay? Both spins, this configuration or this configuration, they both will be the same. Then there are only 3 energy levels. The 2 spins down, the 2 spins up, and 1 up, 1 down, and 1 up, 1 down. That gives you immediately that the lower number is 1. In between, there are 2 energy levels. Therefore, the population, you can see that the ratio 1:1 will slowly be seen from that perspective. We will see all of that more in mathematics in the next few minutes. Now, if you have 3 spins, how many energy levels are possible? Think about it. You should know. You should immediately calculate. See, 1 spin, you have up and down. You put another spin, you add up and down to this. Therefore, 2 became 4. Now, the 4, if you put the 3rd spin with up and down, will become how much? There are 4 to start with. And all 4 can go with the 3rd spin this way. All 4 can go with the 3rd spin this way. So how many are there? 8 energy levels are possible. If you put 4 spins, 2 raised to 4. 1 spin is 2, 2 raised to 0. 2 spins, 2 raised to 1. Sorry, 1 spin is 2 raised to 1. 2 spins, 2 raised to 2. 3 spins, 2 raised to 3. 4 spins, 2 raised to 4. And so you can see that the multiplet of spins depend on how many spins are interacting either weakly or strongly with each other. Okay? So if you put a carbon-hydrogen bond connected to another carbon-hydrogen bond, it's possible for the 2 hydrogen spin 1/2s, to interact with each other. So they are 2 spin 1/2s. Now, if in this carbon you have a CH2 and then you have the next carbon CH, then this hydrogen can interact with 2 of these hydrogens. This hydrogen or that hydrogen. Both are identical in chemical shifts. Therefore, that becomes what is called AX2 system or AB2 system, depending on how close they are in chemical shifts or how far they are from chemical shifts. So we will see all these definitions now, one by one. Okay, so let me share the screen. Yeah. So we are now looking at the spin-spin interactions, and this is extremely important to understand why the spectral lines are multiplets more than one sharp line, you will get a small line, one sharp line, and one small line. So it's a 1-to-1 or two sharp lines, or 1-3-3-1 kind of 1, 2, 3, 4. So multiplets are there for a single resonance line. Okay, so most 1D spectrum, NMR spectra, consists of individual lines of groups of light called multiplets. The interaction between magnetically active nuclei causes the multiplet splitting of transitions. Okay, so let's compare this with the chemical shift. Let's take the spin 1/2. Okay, so you need a minimum 2 spins for spin-spin interactions. Of course, the spin-spin interactions don't depend on the external magnetic field. Therefore, the multiplet structure is not changed if you go from 100 megahertz NMR to 200 megahertz or 500 megahertz NMR. The multiplets remain the same. It is the chemical shift, which now is through the delta factor, that is also cancelled out. So the gap between the lines will be the same, and the spectral lines in one spectrum line also will be the same. They will not be different. Okay, they are independent of this. And the original proposal for understanding these spin-spin interactions came from Professor N.F. Ramsay, another Nobel laureate in physics, and David Purcell, Edward M. Purcell, who was the first professor to win the Nobel Prize along with Felix Bloch in 1952. They both proposed a mechanism for spin-spin coupling. This is called the J coupling. Okay, so now let us look at the pictures. So one spin-a-half nucleus in a magnetic field. So the energy level of alpha is minus h bar omega naught by 2. Okay, the energy level of beta is plus h bar omega. Please remember, the energy expression is minus gamma h bar h naught. So if the spin is plus a half orientation, it is lower energy. And if the spin is the minus a half orientation, it's a higher energy. Lower energy is negative, minus h bar omega naught by 2. The higher energy is plus h bar omega naught by 2. And the difference between the two is the h bar omega naught, which is the resonance frequency. Now, the presence of a nearby magnetic nucleus of a spin-a-half leads to coupling called the spin-spin coupling. Okay. Now, in the simple case, when the two nuclei have different chemical shifts, the J coupling is usually very small. And you can use first-order perturbation theory in quantum mechanics to understand that. First-order perturbation theory doesn't change the wave functions. It only calculates corrections to the energies due to this perturbation. The perturbation is the coupling between the two spins. So the transition frequency of any spin omega naught is changed to two values, omega naught plus or minus half j. And therefore, you can see that a line is split into a doublet by the presence of a second proton. Okay. The case is that delta 1 minus delta 2, the chemical shift difference is larger than the coupling constant, spin coupling constant. This case is called the AX coupling case. Okay. The one with the larger delta is A, and one with the smaller delta is the AX coupling case. Now, the spectrum for the AX coupling case looks like this. See, the lower energy state for the two spins is both the spins are in plus a half. Now, if this resonance frequency 1 is more than this resonance frequency 2, then you see if you flip this magnetic field, flip the spin, the energy level changes only by this much. But if you flip this spin, the energy level changes by this much. You see that alpha 1 to beta 1, because this is a higher frequency nucleus. Okay, this is a lower frequency. You see, this is alpha 2 to beta 2. Alpha 1 remains the same. So this is flipping the second spin. This is flipping the first spin. But then you see that these two energy levels are different. And obviously, when both the spins are flipped, that energy is higher than all of these, and therefore that is there. So you can see that there are 4 energy levels. Now, the spin 1 transition is alpha 1 to beta 1. corresponding to the same alpha 2. There is also spin 1 transition corresponding to alpha 1 to beta 2 to beta 1 to beta 2. So the second spin remains in beta. Here the second spin remains in alpha. This is called 2 spin 1 transitions. Okay, so the two arrows correspond to alpha 1 to beta 1, depending on whether the second spin is alpha 2 or the second spin is beta 2. These transitions will be plus or minus j by 2, where j is the coupling strength between the two spins. And the other will be minus j by 2. And therefore, exactly the same thing for the second spin. The second spin is affected by the first spin's presence. So what are the second spin transitions? You can see that if you draw the arrow from here to here, alpha 2 to beta 2, keeping alpha 1 constant, and alpha 2 to beta 2, keeping beta 1 constant. So the second spin also has two frequencies, and that also is divided as omega 0 2 plus or minus j by 2. Okay. So the spectral line is split by the presence of a second spin for both the spins. This spin is split into 2. This spin is also split into 2. There is no more a spectral line where there was originally 1. They are on either side of that line. The strong line is omega 0 1 if this was not there. But now it has become 2 lines on either side. You can see that there is no line here, but there is a line here and a line here for spin 1. And the same thing for spin 2 here. You see that it's already drawn here. This is the spin 2 transition. And spin 2 transition is the second spin 2 transition. The splitting between the two is the same. This is j. This is also j. Because the one is minus j by 2, the other one is plus j by 2. So the difference between the two is j by 2 minus j by 2, which is j. Same thing here. Therefore, the splitting of a line to a doublet due to a neighboring spin 1/2 can be generalized when there is more than one spin 1/2 neighbor. For example, this proton now has 2 spin 1/2 neighbors. This proton, CH3, this proton has 3 spin 1/2 neighbors. Now, you see, for a 0 neighbor, there's only one line. When there is one neighbor, the lines become 1 and 1. When there are 2 neighbors, what you need is the 2 neighbors will have these 4 energies. And the one spin is here. Therefore, this will now be split by 3 different processes. And so you will get a line corresponding to a single absorption, 1. And then there are 2. The intensity is 2 for the 2 neighbors. And the spectrum splits like 1 to 1. And if there are 3 neighbors, the spectrum splits as 1, 3, 3, 1. Remember, 1 plus 1 is 2. 1, 2, 1, the sum is 4, 2 raised to 2. 1, 3, 3, 1, the sum is 2 raised to 3. 1, 4, 6, 4, 1, which is 16, the sum is 2 raised to 4. So, depending on the number of nuclei, the split will be 2 to the number of that nuclei. So if there is 1 nucleus, this spin will be split as 2. If there are 2 nucleus, this will be split as 4, but 2 of them will coincide. So that's 1, 2, and 1. If there are 3 nucleus, there can be 8 splits, but of the 8 splits, 3 of them will be the same, 3 of them will be the same, so you get 1, 3, 3, 1. And for 4, you get 1, 4, 6, 4, 1. This is nothing other than a binomial expansion coefficient. And the binomial expansion coefficient for a 2-state problem works beautifully. Okay, so you can see that the basic details of the spectroscopy we will follow soon after this. So you can see that omega 0, 1 in the presence of 2 neighbors has 3 lines, omega naught minus j, omega naught, and omega naught plus j. So the gap between the 2 is j. The gap between the 2 lines here also is j. Okay, and if we have 3 neighbors, you can see that it is 1, 3, 3, 1. There is no line where there used to be a resonance frequency. Here, there is a line. For two neighbors, the resonance frequency is still observed, except that two other lines are also observed. And the intensity of these lines is 1:2:1, meaning that there are double the amount of transition frequencies here corresponding to the transition frequencies here corresponding to the transition frequency here. Therefore, the intensity is double up here. In this case, the intensity is tripled, but the total intensity corresponds to 8 energy levels possible. Okay, so all of this can be done using a first order quantum mechanical analysis. Okay, now let us see if we can do that. Before I start that lecture, okay, maybe we can stop for a break. Okay. Have a small break. It is right now 9:50 your time, and be here before 10. Okay, take about 5 to 10 minutes. The next lecture is a long lecture, and it's quantum mechanical. So my question is, all of this is familiar to some of you, right? The others are seeing it for the first time? Yes? Okay, good. It is important. See, when you come here, when you come to learn something, spending your time otherwise at home or otherwise in your college, instead of that, you come here and you spend 15 days or 20 days, you should be loaded by the time you go back from here with a lot of information, a lot of knowledge, and a lot of questions in your mind, because all of us are spending our money, time, government money, your time, and the very purpose for doing that is to introduce you to the more advanced, and sometimes we call it elementary, but it's still slightly more advanced than what most students would do. Therefore, you must keep your eyes and mind open and try to pick up as much as you can, and then go back and sit like a cow and start looking at everything that you had taken. Slowly take it back and read it again and bring it back, like the way cow eats its food. It takes everything that's available in that period. Doesn't necessarily digest all of them, but then it takes time to sit down and relax and digest and also sleep at the same time. Okay, so something like that you should do. We will stop here.
Swayam Prabha, Digital India, Educated India.